Welcome to the Deep Dive. We're here to explore some really fascinating ideas, cutting through the noise. Today, we're taking a deep dive into, well, the mind of Albert Einstein. I mean, the name itself just means genius, doesn't it?
It really does. He completely reshaped how we see the cosmos.
Yeah.
And, he got that Nobel Prize, but maybe not for what you'd expect.
Exactly. So our mission today, it's not just what he discovered, but really how he thought, why some things he called mistakes turned out to be, well, incredibly spot on.
Yeah, and how his unfinished work is still driving physics today. We've looked at biographies, his actual papers, and what experts are saying now about his theories.
It's about getting that deeper picture, right? The genius, the big philosophical questions he raised, and how it all connects to today's cutting-edge science.
Definitely. It goes way beyond just relativity.
Okay, so let's jump right in. Einstein, this brilliant mind. How did he often get his biggest ideas, not from, super complex math, but from simple physical pictures, these thought experiments? Yeah.
It's one of those amazing things about him. Take his happiest thought. He was 16, right?
16, yeah.
And he imagines himself racing alongside a beam of light. Just pictures it.
Okay.
And he thinks, well, if I could keep up, the light beam would look frozen, like a wave just sitting there.
Which doesn't happen.
Exactly. It made no sense to him. Light always travels at the same speed. It doesn't just freeze next to you. And that simple visual, paradox, that inconsistency, it directly pushed him towards the idea of light's constant speed, which, well, that's the heart of special relativity.
So these Gedankenexperimente, these thought experiments, they were like his mental lab. What about the man falling off a roof? How did that simple picture lead to something as huge as general relativity?
Right. Or think about being inside a falling elevator. You'd feel weightless, wouldn't you?
Yeah, totally weightless. Like an astronaut.
Exactly.
Yeah.
And Einstein realized, wait a minute, inside that falling elevator, you can't tell if you're falling due to gravity or just floating weightless out in deep space. There's no experiment you could do inside to tell the difference.
Okay. So gravity and acceleration, they feel the same.
Precisely. That's the equivalence principle. And that simple idea, born from that mental picture, became the absolute foundation for general relativity, his theory of gravity.
It's like the sources say, he preferred thinking in these pictures, trains, elevators, clocks, not just incomprehensible mathematics.
And those pictures guided him faultlessly, as one source puts it. They were his key.
So what does this mean for us today? We've got supercomputers, incredible labs. Does this imaginative, sort of intuitive, what-if thinking still matter?
I think absolutely. It's a reminder, isn't it, that big leaps often come from seeing the problem differently, from imagination, not just crunching numbers. Visualization is still powerful.
Okay, so from those amazing leaps of imagination, sometimes even Einstein thought he'd stumbled. Let's talk about his famous biggest blunder, the cosmological constant.
Ah, yes, the blunder that wasn't. It's such a fascinating story. He introduced it back in 1917.
Why? What was the thinking?
Well, back then, pretty much everyone believed the universe was static, just there,
Yeah.
unchanging. But Einstein's own equations for general relativity, they actually predicted a universe that was either expanding or contracting.
So his math didn't fit the accepted view.
Right. So he basically added this term, the cosmological constant, to kind of force his equations to produce a static universe.
Yeah.
To make them fit what everyone thought was true.
Like a mathematical fudge factor. And he regretted it later, right? Called it his biggest mistake.
He did. Biggest blunder of my life, he apparently said. But here's the incredible twist. What Einstein threw away as a mistake, modern cosmology now calls it dark energy.
Dark energy, the stuff driving the universe's expansion.
Exactly. Not just expanding, but accelerating expansion. And it might be the single biggest chunk of mass energy in the entire cosmos.
Wow. So his mistake actually predicted something fundamental we only discovered decades later.
Pretty much. And what's wild is that almost right away, other scientists, Willem de Sitter in 1917, then Alexander Friedman, Georges Lemaitre a bit later, they found solutions to Einstein's original equations, even with the constant, that showed expanding universes.
So the math was pointing towards expansion all along.
It seems so.
Yeah.
They were showing the universe wasn't static, even as Einstein was trying to hold on to that idea.
Okay, so if dark energy is real and it's pushing everything apart faster and faster, what does that mean for the end game? The fate of the universe? Are we talking big crunch or big freeze?
That's the billion-dollar question, isn't it? It really depends on how much stuff, matter, and energy there is overall, what we call a critical density.
Right.
But this dark energy, this accelerating push, It definitely seems to be pointing us towards a big freeze. The universe just keeps expanding, getting colder, emptier, indefinitely.
Chilling thought. Okay, from the cosmos back down to the very small. Einstein also famously wrestled with quantum mechanics, didn't he? His, quote, God does not play dice.
Yes, that really sums up his deep unease, and it sparked this huge, famous debate with Niels Bohr.
Now, he accepted quantum mechanics worked, right? I mean, it explained the atomic world incredibly well.
Oh, absolutely. He acknowledged it was the most successful physical theory of our time. It led to lasers, computers, all sorts of modern tech. He wasn't denying its practical success,
Ugh.
but philosophically, it drove him crazy. The whole probabilistic nature of it, the idea that particles don't have definite properties until you measure them, that an electron could be in two places at once or just randomly jump between energy levels.
It offended his sense of an orderly universe.
Completely. He believed in a deterministic reality where
Yeah.
things happen for clear reasons, not based on probabilities.
And that's where things like Schrodinger's cat come in. That thought experiment seems designed to highlight how weird quantum mechanics is.
Exactly. It takes the quantum weirdness superposition, being in multiple states at once, and applies it to something macroscopic, a cat. Is the cat both dead and alive in the box until someone looks?
It messes with our everyday intuition.
Totally. And you had interpretations like Max Born's saying the quantum math, the wave function, doesn't describe the particle itself, but just the probability of finding it somewhere.
And Heisenberg's uncertainty principle.
Yeah.
You can't know everything precisely at the same time.
Right. You can know where a particle is, but not exactly how fast it's going, and vice versa. Einstein hated this. He famously quipped, "Does the moon exist only when a mouse looks at it?" He felt reality should be objective, independent of observation.
So these Bohr-Einstein debates, they weren't just about physics formulas, they were about the nature of reality itself. Are those questions settled now?
Not entirely. They're still debated. You have ideas like the many worlds interpretation, suggesting every quantum possibility does happen, just in separate branching universes. And then there are attempts like decoherence to explain why we don't see this weirdness in everyday life. The idea is that quantum states quickly get tangled up with their environment, losing their purely quantum nature and collapsing into one definite reality from our perspective. But the fundamental questions about observation and reality still very much alive.
Okay, let's shift gears again. Einstein spent the last decades of his life on something else entirely, didn't he? This grand quest for a unified field theory.
Yes, his ultimate ambition. For about 30 years, he tried relentlessly to find a single theory that could unite gravity, his own theory, with electromagnetism.
And how was that seen at the time?
Honestly, a lot of his peers thought it was kind of, well, a waste of time, a foolish pursuit, some called it. Physics was moving rapidly into the nuclear realm, quantum mechanics was taking off, and Einstein seemed a bit isolated, chasing this unification dream.
But fast forward to today.
And it's the central theme in theoretical physics. The race to obtain a theory of everything, unifying all the fundamental forces, gravity, electromagnetism, the strong and weak nuclear forces, ambitious young physicists. That's their holy grail.
So his unfinished painting, as you called it, really did set the agenda. Were there earlier hints of unification even before him?
Oh yeah, people had wondered about connections. Michael Faraday, the great experimentalist, apparently even dropped magnets off bridges to see if gravity affected magnetism. And mathematicians like Riemann explored if geometry could be the key.
But the Kaluza-Klein theory sounds like a big step.
It was mathematically stunning. 1921, Theodore Kaluza realizes that if you write down Einstein's equations for general relativity, but in 5 dimensions instead of 4,
Okay, adding an extra dimension of space.
Maxwell's equations for electromagnetism just pop out automatically.
Yes.
Seriously, it was incredibly elegant. It suggested electromagnetism might just be ripples or vibrations happening in this tiny, curled-up 5th dimension that we can't perceive directly.
Like fish in a flat pond, only seeing the ripples from rain falling in the 3rd dimension.
Exactly that analogy. They'd see the effect, maybe call it a mysterious force, without realizing the higher dimension it comes from.
But Einstein himself wasn't fully convinced.
He was intrigued by the mathematical beauty, for sure. But he ultimately felt it was maybe just a mathematical fiction. It didn't explain things like electrons or protons, the subatomic particles being discovered.
And maybe he lacked that guiding physical picture he usually relied on.
That seems likely. Plus, crucially, the properties of the nuclear forces weren't really understood until decades later. He was trying to unify forces when some of the key players weren't even properly known yet. He was ahead of his time, maybe too far ahead of the available data.
So his failure was partly a matter of timing and incomplete
I
knowledge.
think that's fair to say.
And now, today's theories like superstring theory or M theory, they pick up right where he left off, but with even more dimensions.
Exactly. They propose maybe 10 or 11 dimensions, and instead of point particles, the fundamental constituents of reality are seen as tiny, vibrating strings. Different vibrations correspond to different particles and forces.
Unifying everything.
That's the goal. It's a direct continuation of Einstein's dream. These theories even suggest that the forces we see, like gravity, are sort of forced upon us. They had to exist for the theories to be mathematically consistent. It's a profound idea.
Let's circle back to general relativity itself for a moment. Newton saw gravity as this instant force reaching across space. Einstein's idea was radically different.
Completely different. For Einstein, gravity isn't a force in space-time. It is the curvature, the bending of space-time itself, caused by mass and energy. Massive objects warp the fabric of space-time around them, and other objects follow those curves.
And this radical idea led to predictions he couldn't possibly have tested himself back then, like the bending of starlight.
That was the first big one. His theory predicted that light from distant stars should bend as it passes near a massive object like the sun.
And Arthur Eddington's expedition in 1919.
Confirmed it during a solar eclipse. They measured the apparent shift in the star's positions near the eclipsed sun. The measurement, about 1.79 arc seconds, was incredibly close to Einstein's prediction of 1.74.
I read that the atmosphere at the announcement was electric. J.J. Thomson called it one of the greatest achievements in the history of human thought.
It really cemented Einstein's fame and the power of his theory. But the predictions didn't stop there.
What else came out of general relativity that's been confirmed since?
Well, there's gravitational redshift, the idea that light actually loses energy, shift towards redder wavelengths as it climbs out of a strong gravitational field.
Like climbing uphill tires you out.
Sort of. And a Town-Rebke experiment in 1960 measured this effect very precisely right here on Earth, using gamma rays set up and down a tower.
Okay, what else? Black holes.
Black holes, yes. They emerged as mathematical solutions to Einstein's equations way back in 1916, thanks to Carl Schwarzschild. Objects so dense that their gravity warps space-time so much, nothing, not even light, can escape.
Purely theoretical then, but now.
Now we routinely observe them indirectly, and we've even imaged the shadow of one. Roy Kerr later found solutions for spinning black holes in 1963, which seemed to be the norm.
And the latest triumph? Gravitational waves?
Ripples in space-time itself. Einstein predicted them too, caused by cataclysmic events like black holes merging or neutron stars colliding.
And observatories like LIGO.
LIGO and its partners, yeah. A massive project, incredibly sensitive detectors. They made the first direct detection in 2015, opening a whole new window onto the universe. It's arguably the most expensive project the NSF ever funded, around $292 million initially.
So looking at the big picture, all these confirmations, sometimes decades later, it's just stunning proof of his theory's power, isn't it?
It's an incredible testament to the predictive power of theoretical physics when guided by deep principles. The math described reality long before we had the tools to see it directly.
Okay, building on that warping space-time idea, let's loop back to those hidden dimensions and maybe even parallel universes. You mentioned Kaluza-Klein theory.
Right, that amazing insight that adding a fifth dimension to Einstein's gravity equations could automatically give you Maxwell's equations for electromagnetism.
The implication being.
That maybe the forces we experience, which seem distinct, are actually manifestations of geometry in higher dimensions we can't see. These extra dimensions might be curled up, incredibly small, influencing our world in ways we perceive as forces.
Back to the fish in the pond analogy.
Exactly. They feel the ripples, the force of the rain, but don't see the third dimension it's coming from. So perhaps forces like electromagnetism, maybe even the nuclear forces, originate in these hidden dimensions.
And modern theories like M theory take this further, suggesting our whole universe is like a sheet, a membrane.
Floating in a higher dimensional space, maybe 11 dimensions in total. That's the picture M theory paints.
And gravity might behave differently in this picture.
One intriguing idea is that gravity, unlike the other forces which might be stuck to our membrane, could potentially leak or propagate into these extra dimensions. This could even explain why gravity seems so much weaker than the other forces.
Okay, so how on Earth do you test for things you can't see, like extra dimensions or parallel universes?
That's the challenge. We look for indirect clues. One way is to test gravity at very, very small distances, like fractions of a millimeter. If Newton's inverse square law breaks down slightly at those scales, It could hint that gravity is leaking into extra dimensions.
Tiny deviations from what we expect.
Precisely. Another idea, even more speculative, is that dark matter. That mysterious stuff making up most of the universe's mass that we can't see might actually be ordinary matter residing in a parallel universe, right next to ours in a higher dimension. We can't see it, but we feel its gravity.
Wow. And particle accelerators like the LHC?
They could potentially play a role too. If these theories involving extra dimensions or supersymmetry are right, the LHC might create new exotic particles, sometimes called sparticles or Kaluza-Klein particles, that only exist because of these hidden aspects of reality. Finding them would be huge indirect evidence.
Okay, one last really mind-bending area. Einstein's view on time itself. He said something like, the distinction between past, present, and future is just an illusion.
Yes, for us physicists, he wrote, the distinction between past, present, and future is only a stubbornly persistent illusion. A pretty radical statement.
What did he mean by that? How did his theories lead there?
Well, his theories of relativity fundamentally changed our understanding of time. They showed time isn't absolute and universal. It's relative. Depends on your motion and on gravity.
Like time dilation, time slowing down for moving objects.
Exactly.
Yeah.
And that's not just theoretical. They tested it in 1971 with super accurate atomic clocks on airplanes. The clocks that flew around the world did end up slightly younger, showing less elapsed time than the ones left on the ground. Time literally passed slower for them.
So time is malleable, and his equations, they even allow for possibilities like time travel.
Mathematically, yes. Some solutions to his general relativity equations contained weird possibilities. Kurt Gödel found a solution in 1949 describing a rotating universe where you could theoretically travel back into your own past.
Whoa.
And then there's the concept of wormholes, or Einstein-Rosen bridges, theoretical tunnels through space-time connecting distant points, or potentially different times. Kip Thorne explored how, if you could manipulate exotic stuff called negative energy, you might be able to create a stable wormhole.
How would that work for time travel?
The idea is you create a wormhole, then take one mouth of it and accelerate it to near light speed and bring it back. Because of time dilation, less time would have passed for the moving mouth. So, stepping through the wormhole could potentially take you back to the time when the other mouth existed, theoretically.
But this isn't something we can just go build, right?
Oh, definitely not. Stephen Hawking initially argued against it with his chronology protection conjecture, basically saying the laws of physics would conspire to prevent time travel paradoxes.
Like going back and preventing your own birth.
Exactly. Though later, Hawking seemed to soften, suggesting time travel might be theoretically allowed by the equations, but probably practically impossible due to the insane amounts of energy, stability issues, and the need for things like negative energy, which we don't know how to make or control. So, firmly sci-fi for now.
But if Einstein's perspective holds true, if past, present, and future are all part of one block of spacetime, what does that mean for us? For free will, causality, history?
It raises profound philosophical questions, doesn't it? If the future already exists, in some sense, within the space-time block, does that undermine our feeling of making choices freely? Does causality just become a pattern within the block? Does history become less of a flowing river and more of a fixed landscape? These are questions physicists and philosophers still grapple with, stemming directly from the implications of Einstein's view of time.
It really makes you think differently about, well, everything. What an absolutely incredible journey through Einstein's mind and his legacy. From those simple pictures to space-time, quantum weirdness, and time itself.
It really is vast. And I think his true legacy, beyond founding relativity or being a sort of reluctant godfather to quantum theory, was really setting the stage for unification, that search for the deep symmetries underlying nature's laws.
Paving the way for today's theories like supersymmetry.
Exactly. Theories aiming to finally connect matter and forces into one coherent picture. He started that modern quest for a theory of everything.
You know, Einstein famously said, God is subtle, but not malicious. But apparently, late in life, struggling with unification, he told an assistant, I have thought once more. Perhaps God is malicious.
A moment of frustration from a lifelong optimist. He never found that unified theory, but the quest he began is arguably the driving force of fundamental physics today.
So maybe a final thought for everyone listening. Next time you look up at the stars, think about it. Are we just seeing the surface? Could there be hidden dimensions wrapped up or faint echoes from parallel universes nearby? All part of that grand cosmic tapestry Einstein dreamed of describing with a single, elegant theory.
Keep asking those big questions. Keep exploring. That's certainly in the spirit of Einstein.